Hi everyone, I am very honored to present my contribution, which is entitled DFT and DFT plus U study on metal aggregates adsorption on anatase titanium dioxide 101 surface. The presentation plan is as follows. I will start with an introduction. I will then chain with the description of the computational method used. Then I connect directly with the presentation of our results show, which are divided in two major parts. The first is the study of structural and electronic properties of bulk and clean 101 surface. The second relates to the adsorption of metal small aggregates on anatase 101 surface. Finally, I will end with a conclusion. Since the discovery by Fujishima that titanium oxide photocatalyzed the decomposition of water, and due to its chemical stability, non-toxicity and low cost, the titanium oxide gained interest. When a photocatalyst is exposed to light of the desired wavelength, the energy of photon is absorbed by an electron of valence band and it is excited to conduction band. In this process, a hole is created in valence band. This process leads to the formation of photo-excited state and electrons and hole pairs is generated. This excited electron is used for reducing an acceptor in which a hole is used for oxidation of donor molecules. And the generation of the electron-hole pair can be written as follows. Photocatalysis has been widely applied in various areas, such as solar cells, water splitting, and others. However, bare titania still has some inherent limitation due to its band gap energy that is 3.0 to 3.2 electron volts. So it can only absorb UV radiation, that is 5% of sunlight. Also, another key issue encountered with titania is the higher rate of recombination of electron-hole pairs, which causes to reduce the activity. In order to overcome these drawbacks, doping or incorporating metal atoms to the titania structure has been introduced. So platinum is one of the most studied metals on single crystal titanium surfaces, and a recent research shows that addition of alkali metals ions significantly promotes the activity of platinum on titanium dioxide catalyst. And in this presentation, we will focus on the interaction of platinum dimer and platinum sodium clusters with the 101 surface on the anatase polymorph of titania. Our DFT calculations were performed with PBE functional of the generalized gradient approximation as implemented in VASP code. Electron-ions interaction were modeled by the projector augmented wave method, with these configurations treated as valence electrons for titanium and oxygen. VASP package uses plane wave basis set where a cutoff energy of 520 electron volts was considered to expand valence electrons in our calculations. With reference to anatase, the most photocatalytically active titania polymorph, it exhibits a tetragonal crystal structure where oxygen atoms form edge-sharing distorted octahedra. Half of these octahedra are occupied by titanium atoms, while the other half are vacant. The lattice parameters of bulk anatase titania were calculated close to the experimental values, with a relative error of 0.66% and 2.39% for E and C respectively. The computed bulk moduli of anatase was calculated with an error of 6.22% relative to the experimental value. The band gap was estimated with an error of 32.81% relative to the experimental value. It is known that the band gap of transition metal oxides is underestimated with the conventional DFT approaches. They are inappropriate for characterizing the semiconductor with open shell electrons localized in the d orbital, which is largely due to the self-interaction error in approximate exchange functional. So the FT plus U approach is suggested to improve such localization efficiency. And this approach consists of incorporating effective intra-atomic column and one-site exchange term by introducing U effective parameter. The optimization of U effective parameter shows that the value of 6.7 electron-volt produces the experimental band gap as shown in density of state figure of titania anatase. The figure on the right shows that 3D state of titanium atoms plays a dominant role in the conduction band, while 2p states of O atoms are more included in the valence band. To study metal aggregates adsorption on titania anatase 101 surface, we will first investigate its relaxed structure. On the basis of our calculated results, we found that both 5-fold coordinated titanium atoms and 2-fold coordinated oxygen atoms are present on the first layer of the surface layer, and also there are both 6-fold coordinated titanium and 3-fold coordinated oxygen atoms on the second layer of the surface layer, as shown in the figure. The results of the relaxation of the anatase 101 surface, modeled as an infinite stack of 3-layer slabs separated by a vacuum of 15 angstrom, indicates significant displacement of the surface atoms. The coordinatively unsaturated 2-fold oxygen atoms and 5-fold titanium atoms tend to tighten their bonds with nearest neighbors. Finally, the distance between 2-fold coordinated oxygen atoms and 5-fold coordinated titanium atoms is slightly elongated after relaxation. We can note that our results are in good agreement with other previous calculations. The calculated band structure of anatase shows a little effects on the electronic properties, that is band gap, compared with those of anatase titania-Berg structure. As same as Berg calculation, when the U correlation is considered, the value of the band gap increases from 2.30 to 3.28 electron volts, as shown in the figure of the density of state of anatase surface. In order to study the metal aggregates adsorption on the relaxed surface, we have considered a 3-1 unit cell, and for a single platinum atom adsorption, the most stable site is the bridge site between two oxygen 2-fold, where the adsorption energy is minus 2.84 electron volt. It is also observed that platinum adsorption changes the platinum oxygen bond length. The calculated density of state of platinum on titanium oxide system is shown in the figure. Top panels correspond to platinum on anatase surface, and the bottom panel to the anatase clean surface density of state. The Fermi level is at 0 electron volt. The adsorbed platinum atom introduces 3 new states close to the Fermi level, which can be clearly observed in the density of state. The calculated adsorption energy for platinum dimmer is in good agreement with previous other calculations, and the platinum dimmer increases the platinum bond length. The calculated total density of state of the most stable platinum dimmer absorption configuration shows that the state introduced by platinum adsorption shift to a lower energy state as the number of platinum atoms increases. There are 2 possible configurations for platinum-sodium adsorption on anatase surface, perpendicular and parallel to the titanium-oxygen bond plane. The horizontal induces a dissociation of the platinum-sodium aggregates, while the vertical configuration is found to be stable with an adsorption energy of minus 1.85 electron volts. After the platinum-sodium aggregates absorption, the electronic structure undergoes deep changes because of the strong shift of the platinum-induced state toward the top of the valence band. In conclusion, DFT calculation have been performed on the 101 surface anatase in order to examine the effect of platinum dimer and platinum sodium cluster adsorption of anatase surface properties. And the results show the strong interaction between the adsorption metal aggregates with the titania 101 surface, which is targeted by the introduction of new states close to the Fermi level after platinum atoms adsorption, and the strong shift of the platinum induces states toward the top of the valence band after adsorption of platinum sodium cluster. We believe that these new states close to the valence band may improve the photocatalytic properties of titania. I thank you for your attention.